So in this lecture, we are going to talk about special cases that occur while we apply the Routh test on certain characteristic polynomials. These are two types of cases that we encounter generally. So the first case is, I'll illustrate with the help of this example. The first case is when there is 0 in the first column of a row. So when this happens, we are unable to proceed as far as completing the Routh table is concerned. So here we have this characteristic polynomial qs is equal to s5 plus 2s4 plus 2s cube plus 4s square plus 11s plus 10. Let us complete the Routh table for this. So we start with the fifth degree term and we take the alternate terms and fill up the table. So you have the coefficients here 1, 2 and 11, and then the even terms. So 2, 2 here, 4 and 10. And let us put 2 zeros here in order to complete the table beyond certain some of the coefficients. So now, in order to evaluate this this term here, we have to find the determinant, and as you can see, the determinant here is going to be 0. And this term here, the second one, is this determinant, right? So that is going to be 20 minus 22 divided by minus 2. So that is going to be it's going to be 10 minus 22 divided by 2 with a minus sign, so this is going to be 6, and this term here is 0. Now the problem that has suddenly cropped up is that this term here is 0, and in order to find the coefficients, in order to find the entries in this table, this is the term with which we have to divide the determinants that we have, right? So what to do? So the solution that is given, that is prescribed, is that we replace this 0 with a number which is very close to 0, and we call that number epsilon, right? So we replace this with epsilon, right? And then we try and complete the Routh table, assuming epsilon to be extremely small and assuming that it is tending towards 0 either from the positive side or the negative side. So if you complete this table beyond this now, you see that this term that we get here in terms of epsilon in this bracket would be given by this determinant. So this is 12 minus 4 epsilon divided by epsilon with a minus sign, which is 4 epsilon minus 12 by epsilon. And you can write this as 4 minus 12 by epsilon here, right? And this term here is going to be found by finding this determinant, and this will be straight away because this point here is 0, this term here is 0, so this will be just 10, right? And then you can complete a 0 here. Now the next row is found by again finding the determinant like this, and you can see that this term here is going to be calculated. So this is going to be 10 times epsilon minus 6 into 4 minus 12 by epsilon divided by 4 minus 12 by epsilon, right? With a minus sign, of course. So this is going to be 10 epsilon divided by 4 minus 12 by epsilon. Take the minus sign outside, minus 6, and let us simplify this term here to get, this is going to be plus 6. So this is 6 minus 10 epsilon square divided by 4 epsilon minus 12. So let us call this as some term C and put this C here in the table that we have here, C. And for the next term, we have to find this determinant here, which is going to be 0. So then the next row, so this will be this determinant. So this entry being 0 here, so we'll just have this entry coming up here, 10, 0, 0. So now we have now we have the first column in front of us. The first column is here 1, 2, epsilon, 4 minus 12 by epsilon, C, which is 6 minus 10 epsilon squared divided by 4 epsilon minus 12, and 10. Now we have to see what is going to happen if epsilon is tending towards 0, and let us assume that it's tending towards 0 from the positive side. That is, it is a small, very small positive number. So in case that happens, uh, we make that assumption, then this term is positive, this term is positive, this term is positive because epsilon is positive, and this term here is negative because 12 by epsilon is going to be a huge number, it's going to be a big number, and it's negative. So adding it to plus 4 will still not change the sign, and it will remain a negative number. And now let us look at the sign for C, which is here 10 epsilon square divided by 4 epsilon minus 12. So this term that we have here is going to be a very small number because you have epsilon square in the numerator as compared to 6, right? So so it's going to be 6, even if we assume that it has some magnitude, it is still going to be very small, and it's still going to be a positive number because 6 is going to be roughly equal to 6 plus 10 epsilon square by 12, because you can always ignore this 4 epsilon with reference to this minus 12, and it's still going to be a positive number. So in any case, if you look at this whole thing, then you can ignore this number because it's a very small number. It's a multiple, it's being multiplied by epsilon square. So this term here is going to be positive, and this term is again positive. So one can see that there are two sign changes, right? And one can easily discern that there are two poles in the right half plane. So the same strategy can be applied if we assume epsilon to be tending towards 0 from the negative side. But any one of the tests is okay, so we can always do this and get the result that we actually want to get. So basically, this case is for the case when there is 0 in the first column of a row, right? And in that case, we just replace the 0 which is in the first column of the row by an entry which is very small and which is called, right, which we can which we can symbolize using the uh, the uh, uh, the variable epsilon. Now let us look at the other and the second important case, which is when we actually have the whole row which becomes 0. So when the whole row becomes 0, then the thing becomes slightly different. So let us take an example for this. So we have this QS is equal to uh, S S5 plus S4 plus 4S cube plus 24S square plus 3S plus 63, right? And let us try and make the Routh array for this. So we have this S5, S4, S3, S2, S1, and S0. And let us try and complete the Routh array for this. So the first two rows we just write down by inspection. So this is 1, 4, 3, 1, 4, 3, and then 0. And the second row again by inspection. So this is 1, 24, 63, and 0. And now let us try and find out the third row, which is going to be the determinant that we have here. So this is 24 minus 4 divided by 1 with a minus sign. So minus 20. Again 63 minus 3 divided by 1 with a minus sign. So minus 60, 0, and 0. Now let us look at this row that we're trying to find. Minus 60 minus 20 into 24 divided by minus 20. So if you calculate this you're going to get is 21 63, and 0, right? And now, if you look at this row that you have minus 21, minus 20 into 63, plus 21 into 63, this row here, this element here, this is going to be 0. This whole row is going to be a 0. So now this situation is slightly different from the situation that we had in the previous thing. The situation in that case was that one element was 0, and in this case the situation is that the whole row is actually 0. So this happens when there is an even polynomial which is a factor of the actual polynomial for which we are finding the Routh table. So this condition, when there is a whole row of zeros, is there when there is an even polynomial with which is purely which is a purely even factor, which is a factor of uh, even polynomial which has with roots that are symmetrical about the origin. So you have an even polynomial which has roots that are symmetrical about the origin, and this polynomial generates uh, an entire row of zeros. And this even polynomial is actually a factor of, so this is a factor of the characteristic polynomial QS, right? So the roots, like for example, could be like s square plus 1 is an even polynomial, which s square plus 1 is equal to 0 has roots which are symmetrical, plus minus j. Similarly, s4 plus 1 equal to 0 is an even polynomial which has roots like this, plus j, plus 1, and minus 1. So these are examples of even polynomials which have roots which are symmetrical around the origin, and these cause the rows of zeros. So what we do in this case is to try and find the polynomial, which we call the auxiliary polynomial, or the auxiliary equation if you try and equate it to 0. So that is found by taking the row just above the row of zeros and then writing the polynomial for this. So here you can see that if you take the row just above the row of zeros, the polynomial that you get is 21 for the s square term, and then since we skip 1 degree, so it is 21 s square plus 63. So the polynomial, the auxiliary polynomial, is 21 s square plus 63. This is the polynomial that is causing the row of zeros to actually come up in the Routh's array. So what we do is that we differentiate this polynomial and then replace the coefficients of the row of zeros with the derivative terms. So you get 42s. So what you're basically going to do is to replace this with 42 here, and then try and complete the Routh table. So once you replace this with 42, you automatically get 63 at the end, and then you can complete the Routh table. So this is how we have completed the Routh table, by differentiating the auxiliary equation or the auxiliary polynomial, and then writing the terms of the derivative of the auxiliary polynomial in the row of zeros, and then completing the Routh table. Now, then we can look at the sign changes. Now, one thing that has to be understood in this is that this portion of the Routh table corresponds to the auxiliary polynomial, right? And the portion that is just above it, right, corresponds to the rest of the polynomial which is obtained once you divide the actual polynomial by the auxiliary polynomial. So by the auxiliary polynomial. So the number of sign changes in this would correspond to the sign changes in this would correspond to the number of right half poles in the auxiliary polynomial, and the number of sign changes in this would correspond to the number of poles in what is left after you divide the characteristic polynomial with the auxiliary polynomial. So you can see in this that there are no sign changes in this part. So all this is plus plus, then it's minus, and then again it's plus plus plus. So there are no sign changes in this. So although this auxiliary polynomial is present, but there are no poles in the right half. That means there are two poles and both of them are on the j omega axis, and that is also clear from this uh, polynomial which we have. If we have to factorize it, we can see that 21s square plus 63 equal to 0. If you try to find the roots, this is equal to s is equal to plus minus j root 3. So these are the two poles corresponding to the second degree auxiliary polynomial. So that is why we don't see any sign change in this part of the Routh table, right? So we can conclude that two poles are on the j omega axis. And for this part of the Routh table, we see that there is one sign change there from here to here, right? And then we can conclude that from here to here there is no sign change, from here to here there is one sign change, and from here to here there is another sign change. So there are two sign changes in the part of the polynomial that is obtained after we divide the characteristic polynomial by the auxiliary polynomial. So we can conclude that there are two right half poles, there are two j omega poles, and since a 5-degree polynomial, there is one pole in the left half plane. As simple as that. Please understand that these sign changes correspond to how do we look at the sign changes. So this sign change, let me draw it here. So if you have for example uh, uh, in this case we had three terms corresponding to the auxiliary polynomial. So uh, this part of the Routh table corresponded to the auxiliary polynomial, and this part of the Routh table corresponded to the rest of the polynomial. So this sign change, the first sign, this sign change, this sign change, and this sign change, if there is any, would correspond to the polynomial that is left after you divide by the auxiliary polynomial. And then this sign change here, 1 and 2, these will correspond to what is left after on the sign changes corresponding to the auxiliary polynomial. And since there are two sign changes in this, because this is plus, this is plus, this is minus, so there are two sign changes, one from plus to minus and then from minus to plus. So there are two poles in the right half plane, and since there are no sign changes here, there are two poles on the j omega axis, right? So we can exactly know without factorizing how many polynomials are on the j omega axis and how many are in the left half pole or how many are in the right half pole. Now let us take an example in which both these cases arise together, right? So you have a row of zeros, and you also have a single row which is 0. So this is a slightly complicated example, but we can still do it. This is S6 plus S5 minus 6S4 minus S square minus S plus 6 equal, this is our characteristic polynomial. So when we draw the Routh table for this S6, S5, S4, S cube, S2, S1, S0, you can see that there is no cube term here, so we have to replace that by a 0. So we can write plus in this plus 0 S cube. And let us take now the coefficients that we need to take. So the coefficient 1 and minus 6 and then this one minus 1, and the last one even one, which is 6. And the second the odd terms, 1 here, and 0, 0, and then minus 1 here, and then you can replace this by 0. And now if you make this one, this will be minus 6, this will be 0, this will be 6, this will be 0. Coming to this, you have a 0 here, and you again have a 0 here, 6 minus 6, and then you have a 0. So this, you're getting a row of zeros. So when you get a row of zeros like this, you have to see your auxiliary polynomial, which is just above the row of zeros, right? So this is just above the row of zeros. You can see that your auxiliary polynomial is minus 6s4 plus 0s square plus 6. So this is your auxiliary polynomial. So auxiliary polynomial is going to be minus 6s4 plus 6 in this case, and you have to differentiate this. You get minus 24s cubed. So you can write, instead of this, you can write minus 24 and then try to complete the table. So when you try to complete the table after this, you'll get a 0 here again. And in this term here, you'll get 6 because you're finding this determinant, this into this, and then you have a 0. So here in this, now you have a different case in which you actually have to replace this with epsilon. So you replace this with epsilon and then try to complete the table. So when you replace this with epsilon, you get here, this you get minus 24 into 6 divided by minus epsilon. That gives you 144 by epsilon here, 0 and 0, and here you get 6, 0, 0. So this completes the table. So here in this case, both special cases are together, and now you can look at the part that corresponds to the auxiliary polynomial. So your auxiliary polynomial starts from here, right? It's a 4-degree polynomial. So this portion of the Routh table corresponds to the auxiliary polynomial, and it's a 4-degree polynomial. It's actually minus 6s4 plus 6, right? So the upper part of the table corresponds to what is left once you divide the characteristic polynomial by the auxiliary polynomial. Now let us look at the sign changes. So this is plus, this is plus, this is plus, this is minus, minus epsilon you can take to be tending towards positive sign, epsilon if it's tending to towards 0 from the positive side. So this will be plus, this will be plus, this again is plus, right? So you can also take epsilon to be tending towards 0 from the negative side, then this will be minus, minus, and this again will be plus. So in any case, you will get the same number of sign changes. So here you have, let us look at the sign changes. So you have one sign change here, another sign change here, so 2 sign changes. If you look at the sign changes from the if you take epsilon to be negative, then you have one sign change here and another sign change because all this is negative here. So in both cases you have 2 sign changes. Let us remove this and concentrate on epsilon being positive. So now there is no sign change here. So this sign change here corresponds to the sign change because of the polynomial here, the one which is left when we divide by auxiliary polynomial, and this sign change here corresponds to the change because of the auxiliary polynomial, the presence of the auxiliary polynomial. So let us look at it again in order to clarify it more. Let us look at it again, right? So let's look at the sign changes. So this term is positive. This term is positive. this positive, this is negative, negative, positive, positive, and positive. So, so, so no sign change here, then one sign change which I mark in red, then no sign change here, then one sign change which I mark in red, and then no sign changes, right? So these sign changes, this sign change corresponds, this sign change corresponds to the this part of the Routh array, and this sign change corresponds to this part of the Routh array. So what we can say is that what we can say is that the auxiliary polynomial S has one right half pole. Since it has one right half pole, it also has to have one left half pole because the poles have to be symmetric, right? And since it's a 4-degree polynomial, we are left with two poles, so two poles would be on the j omega axis. And for the rest of the polynomial, since there is one sign change, so the rest of the polynomial has one right half pole, right, and one left half pole. So that corresponds to 2 degrees, which is left after you divide by the auxiliary polynomial. So in totality, you can say that you have how many right half poles? You have 1 plus 1. You have 2 right half poles. How many left half poles? 1 plus 1. You have 2 left half poles. And how many poles on the j omega axis? 2 poles on the j omega axis. Right? So this way we are able to say exactly how many poles are where and whether the system is stable or unstable. So that's all for today. Thank you very much for listening.